Welcome. Let's look at growth and decay. There's a couple of formulas to know. These are exponential things. The growth is going like start slow and that's going up really fast, or it's a high thing and then it starts coming down low like this. That's a decay. Growth and decay, meaning going less. So this is the formula we're going to look at right now, one of the two that we're going to use. And each of these things have a particular meaning, so that Y is the final amount. The letter A means the initial amount, so I'll do final and initial. This R is the rate of change. Has to be larger than 1 in this one. It's a positive number. This is a plus here. This is the growing one. And it can be a decimal as well. And then we'll look at that T is time. Sometimes it might be minutes, seconds, hours, days, years, depending upon whatever the problem is. Now, that Y, this is like set up like a function. So you could actually say ft equals a 1 plus r to the t. The reason for that is that this is the result of using a certain time. Whatever the amount of the time is, if you plug that t in, well, the other things you already have, and it will like give you what the amount is at that time. So in a way, we have like a coordinate point. We have time, and then we have y. As time is like x in this case. A different time will give you a different amount. So now, if you have a negative here, that's when r is less than 1. It means you're going down. So this is a growth one. Because of the plus, that means growth. So it's like population growing or an amount of money growing. And this is going down, or what we'll call decay. The other formula we have is actually very similar. Compound interest. So if you invest some money in something, you're either going to make money on it or lose money on it, hopefully make money on it. And it's compounded. So that means you make a certain interest amount in a certain amount of time. Like if you put $100 in investment and you're told you have a 5% rate, interest rate in 1 year, that means at the end of 1 year, they give you $5. So you now have $105. And then you take 5% of that for the next year. But that compounding can be done at other times. So you can have an annual compounding. And see this n that's here? That would be n equals 1, meaning once a year. You can have a semi-annual, and that means twice a year. N would be equal to 2. You get half the interest partway through the year, and then your interest would be for the second half, but it would include that first extra amount of money. You can have a quarterly amount or compounding, and that means like a quarter is 4. Well, it's 4 times in a year. It's like every 3 months. That's 1/4 of the year. Often seen as monthly, and monthly would be every month. So it would be 12 months. There are others too, but these are the most compound ones. There's also a continuous compounding. So like almost like every second, you keep getting a tiny little bit more. But that's not part of this lesson here. It's a different type of formula. And we'll look at that in the future. Right now, however, let's match these things up. The A here is the final amount. It's also the same as if you said Y or the function of T, just like in the problem before. As the time changes, the amount changes. So what we have is T and A, just like above in the problem before, we had T and Y. Here, the A, the amount is like the Y. The P is the principal. Well, I'm going to do that one in color here. That's the principal or initial amount. So in the last problem, that was the lowercase a. I actually want to put this one, just like in the last one. This was yellow. The T is time. Last one I used green. and that's placed here. And that's when you set it up like put in a certain amount of time, you get a certain result. The R, okay, is on top of the N there, and that's the annual interest rate, and you set it up as a decimal, never as a percent. And now we have the N is the number of times the interest is compounded. So it'd be like these N's. And notice there's an N there, and there's an N there. Now, if it's annual, it would be just a 1, which means it would actually be the same as this kind of formula up here. This is the same one as the one below, except we don't have N under it like that. So now I'm going to erase that because we don't have N for the first one. We're going to use both of these formulas based upon the things that we're doing. So let's take a look at this problem. In 2008, Flat Creek had a population of that amount and an annual growth rate of that amount. Write an equation modeling that. So our first job is to write an equation, and then our second job is to find out what the population will be, or now this is a little bit old, was in 2018. And 2008 was the beginning. So what the information we have are two different things here. In 2008, okay, we had the amount of 280,000 people there. That's like a point. 2 and 8, lots of them in there, just coincidental. But one of the things you learn about these problems is that if this is the beginning, you're going from 2008, you're going from 2008 to 2018. That means this is the start. And that means you're counting at 0 to start. So this actually should be written as 0 and then 280,000. So that is like the beginning point we have. Okay. In fact, if we were graphing this, it's like X and Y axis, that would be our Y-intercept, and then it's going up from there. Okay, that's a growth function. So the equation we use, when we look back up here, it's an annual growth rate of this amount. Okay, so we're going to use, it's a growth one, and growth was Y equals A, 1 plus R to the T. Well, what we have here is the A, that's the initial amount, and we have the R. Now, notice something about the R. We can't have it a percent. So what we have to do is take 0.85, remove the percent, and move the decimal twice that way. So in reality, we have an extra leading 0 in front, 0.0085. So that's R. Okay, now, I am going to say Y is equal to 280,000, 1 plus 0.0085, and then the T is the amount of time. Now, if we had put 0 here, this to the 0 power would just be 1 times 280,000. So a 0 time gives us this 280,000 as the result. Let's continue to simplify this one. Y equals 280,000, 1.0085 T. That's the equation. Whenever possible, add those together. There are some times where it's actually easier to keep it separate. We'll go through one of those with the compounding interest ones. So that is A. Now for B, where we have 2008 to 2018 is 10 years, because 8 is the 0, and then 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 2018 is 10 years. So that means T is equal to 10. So let's use this formula. 1.0085 to the 10th power. And then when you calculate that, it comes to this amount, 304,731, and it's 0.39, I think. Now, interesting thing about this one is that you can't have a decimal for people. If it's human beings or animals or something like that, you can't have a partial. So that means you don't round it at all. Your amount of people would be this. So the population in 2018 was 304,731 people. Okay, let's mark that up. Now, an interesting little thing about that, let's say you did a problem like this and the number of people came to 72.9. You would normally round that to 73, but you can't do that here because we don't have 0.9 of a person running around. You just can't count the decimals at all. It's 72 people. If it's a baby about to be born, well, you have to wait till the baby's born before counting as the baby as part of the population. So you have to actually keep it at the, not do normal rounding rules on a practical basis. You would do it for other things. It's just if it's a person or a number of animals, like there's some problems where we have fish or rabbits or things like that, then you can't round up. You simply don't count the decimal point. Now let's look at the next problem. Okay, and first we have to change the number here. That's not supposed to be 280. That's a typo from the last one. It's supposed to be 98,000. This is the same type of problem. So let's go through it and look at it. So in 2018, that's the 0 year, and it's 98,000. And we're going to write an equation and look at the population in 2025. So this is the percent, so that's our R, but we have to move the decimal 2 times and get rid of the percent. So we have 0.0105. Okay, that is going to be the number that we're going to use for R. We have to take the percent and change it to a decimal. This is the A, the original amount. Right? So we're going to use Y equals A, 1 plus R to the T. We have Y is equal to 98,000, 1 plus 0.0105 to the T, and then we'll add that inside the parentheses part, 1.0105 to the T. There is our equation. That's letter A. And then next we're going to use it. So I'm going to use the equation by putting, let's see, from 2018 to 2025. Well, it's a little bit harder to think of the numbers, so let's think about it. Let's do it this way to be safe. The thing to be careful of is that in 2018, that counts as the 0. We haven't done a full year yet. So it's not until 2019 that we get 1 year. And 20 is the second year. 20, so I guess I'll do 20s here. 2021, the third year. 2022, the fourth year. 2023 is the fifth year. 1, 2, 3. 2024 is the sixth year. 2024 is the seventh year. Oh, 5 there is the seventh year. So for 2025, that's 7 years. And that's what we're going to put in T. We want to know for the 7th year what the amount of population is. Okay, so we will take this thing, and this is letter B. We will take this formula, 1.0105 to the 7th power. And when you calculate that, I'll actually give you some numbers, but tell you you'd best to leave it in the calculator, do it all as one thing. That becomes 1 to the 7th power will give you 1.0758. 5, 6, 1, 9, and it continues from there. So you can round that off, but it's better to do this in the calculator and then multiply by 98,000. And if you do that, you're going to get approximately 105,000 433.91. This is the number of people in a city. Therefore, you can't use any decimal at all. So we would say El Cajon will have 105,433 people in 2025. All right, great. That's showing with population how you can use the growth formula to get with a rate and with an initial amount. You can make an equation and then you can solve it for any number of years. Okay, let's go. In fact, I'll write here. Not reasonable to round in case of people, animals, people or animals. Okay, just drop the percent. Now, let's go to a finance problem. You purchase a car for almost $19,000 and it depreciates. That word means it's going down. That means this is a decay problem right there. I see that. It's going down 18% annually. So we have this amount, 18% depreciates. Annually means once a year. And we're going to find it for 6 years. It doesn't say to write an equation, but it's much easier to do this if you do use an equation. So since this is a decay problem, it's going to be just like the growth one, except now there's going to be a minus here. And we know the initial amount and we know the rate, except that we have to change 18% into a decimal. So we move 1 and 2k places because the decimal's after the 8. So 0.18 is that percent. So let's put that in. Y is equal to 18,995. 1 minus 0.18 to the t. We don't know an amount of time yet, but now if we put in an amount of time, we calculate this and we get what the result is over here. So let's clean that up there. 1 take away 0.18 is 0.82 to the t, and there is an equation. Now, we're going to say t is equal to 6. And so let's put a 6 in there. Y equals 18,995, 0.82 to the 6th power. So what we'll get will be 6 years and the amount of money that it's now worth. Calculate in the calculator by putting in this one, 0.82, raising it to the power of 6, pressing enter to get the number for that, and then multiply by the A. And when you do that, you're going to get approximately $5,774.61 and then more. Now, this should be rounded either to the hundredth place, because we deal with pennies in the United States, or you can round it to the dollar. It would be okay, appropriate even if you round it up to there. So both of these are acceptable answers. Not acceptable any other rounding, because we only deal with hundredths and we only deal with dollars as our two main things. So either of these would be considered correct. But now think about what depreciation does here. This car was originally $19,000. 6 years later, it's only it's less than 6,000. It's only not even a third of what it was originally worth. Right? So I was going to put 5775 there. Not money. So that's it, sort of like a point, but this is the solution. Okay, either one of those. Let's do another type of one. Now, this one's also dropping, so this is a decay problem. And it's going down by this much for the rest of the rate. And this year, the amount of donations was this. So this would be our A. Oh, and that's supposed to be a comma here. So it's 390,000. That's the initial amount. and then 5 years from now, so that means we're going from 0 to 5. Okay, so we're going 5 years from now. Because it's a decay problem, we're going to use y is equal to a 1 minus r. Decay means making it to the t. Decay means making that. So let's enter what we already know. 1 minus, the rate. We have to change it, change the decimal, or percent rather. We take that away, but then we move the decimal 2 times, and we put a placeholder in front. So it's 0.011. So 1 minus 0.011 to the t. I'm going to erase that part so I can put the t here. And then I'm going to simplify that number. 1 take away 0.011 is 0.989 to the t. Now, this is the equation. I could put any number of years, but in this case, I want to do that t is equal to 5. So y equals 390,000, 0.989 to the 5th power. Because this is less than 1, every time you multiply to itself, you get a slightly smaller number. When you do this in the calculator, raise it to 5, and then multiply by the 390,000, you get approximately 369,016.74. Okay. So that is our amount of donations. So it went from 390,000 down to 369,000, about $21,000 loss. That's a pretty high percentage for a charity that is trying to help people and doesn't have a lot of money. But the concept here, what you see is we get an equation by filling in the 2 things that we know and working that out, and then putting in the time to figure out what the result is of the time. Same thing here. It was find this equation and then using it, and partly because we put the rate in here correctly. Okay, let's go to an investment problem. You invest $1,000 at 7% compounded monthly. How much money do you have after 18 years? So this is the principal, what we called A before in the original other problems. It's the original amount, or what we call the principal. This is the interest rate, but 7%, we're going to have to move the decimal twice, so it's 0.07 for the R. It's compounded monthly. That means 12 times. That N is equal to 12. In fact, let's take a look at the formula here. The amount that you're going to have is going to be the principal times 1 plus R over N to the N times T. So we figured out everything but T and A, and that's because the amount of time will give you an amount of money. And we don't know what that time is yet to force the amount of money, the amount there. Instead, we do know that we can fill in these things. P, R, there, and then N. So A is equal to $1,000, 1 plus 0.07 over 12, and then 12 T, because we don't know what the T is. 12 is the N. And now we would do some calculating. So you can put this in the calculator and you would get 1.005833. However, it's better just to simply put it in yourself. Put it in, let the calculator give the number n plus 1, and you would have whatever that is. We're going to leave it like this, though, because I don't want to round it off. That's going to make it less accurate when we do put a time in. So we can accept this formula. Okay, Now, we know that the T is 18 years. So T is equal 18. We're going to want 18 and the amount of money that we'll make in the 18th by the 18th year. So let's put that in. 1,000 1 plus 0.07 over 12, and 12 times 18. So 12 times 18 is 216. I'm just going to write 216 here. And so I would put this in the calculator, add 1 to it, and then raise it to the power of 216. Then, hold on, something went away. We're back. Raise it to the power of 216 and multiply by the 1,000. And what you would get, the amount would be approximately $5,917.20. Oh, wait a minute, I have the wrong one. Hold on, I wrote that number from somewhere else. It's still a pretty significant amount. $3,512.50, which could be rounded, or $3,513. Because at that large amount, the actual pennies don't really mean so much. So this is acceptable, or this is acceptable. And think about where it came from, that originally you just put $1,000 in and you let it sit there for 18 years. You end up getting an extra $2,500 for being patient. In fact, now I'll write here 3,513, because it is like that, like points on a graph. If I put 19, this would be a little higher. 20, it would be a little higher, and so on and so on. Every year more would give you more amount. Let's take a look at another investment problem. The same 1,000, but here, this was a 7% interest rate. This is the same, almost the same thing, except there's two things changing. 10%, and instead of monthly, it's now quarterly. Well, quarterly means 4 times. 10% interest rate, we'll take the decimal and move it twice, 0.10, but we still have $1,000. So let's use the formula. A is equal to P, 1 plus R over N to the NT. Well, we don't know what the amount is, but we know that the principal is $1,000. 1 plus the interest rate is 0.1. And then quarterly is 4 times. And then this is 4t. So we have an equation. And if I'm given a certain t, that will give me back a certain amount over here. Right? And we are given, again, 18 years. So that means this is going to be 18 years. So let's put an 18 in. A equals 1,000. 1 plus 0.1 over 4. And then here we have 4 times 18. Ooh, going to be a little bit of conflict there. All right. You could actually play with this one, because it's divided by 4, will give you an exact answer. It gives you 0.025, which means it's 1.025 inside there. You can still just use the calculator to do that each time that you're using the problem. But now, if I raise that to the power of 72, okay, let's actually write that out here. 1,000, 1.025 to the 72nd power. And that gives us an amount of approximately $5,917.23. Okay, now let me point out something for this. I can get this so it doesn't disappear. Oh, there's not too many. Oh, no. Okay, now I think I have enough here to not worry about it. Look at 7% interest, and monthly compounding is usually better, but the difference between 7% and 3%, so 10%. At 7% for 18 years, you add 3,513. At 10%, you get 5,917. A huge difference by the percent rate. So every percent 1% higher, then you get higher results. And that concludes using these two formulas for growth and decay problems. I hope it made sense and hope it helped you. Thank you for listening and watching.